All right, Chapter 10, Flow Rates and Durations of Enteral and Intravenous Infusions. Okay, our objectives this time, describe the basic concepts and standard equipment used in administering enteral and intravenous infusions. We'll talk a little bit about the equipment. Converting flow rates between GTT per MIN, so that's drops per minute, and milliliters per hour. We know those units. Calculate the flow rates of enteral and IV infusions and calculate the durations, so that would mean the time, and then determine the fluid replacement volumes. Okay, so intravenous and enteral solutions. If you're going to be administering the medication through a vein, it's intravenous, and through a tube would be enteral. Enteral feedings. So tube feedings provide nutrients and other fluids by way of a tube inserted directly into the gastrointestinal system. So the fluids can basically flow continuously or intermittently, but if it is continuously, you don't want to exceed 24-hour periods at a time. Orders will always indicate a flow rate, where the flow rate is the volume of fluid to be infused over a period of time. So you notice our nice equation set up down here at the bottom. So the flow rate equals the volume over time, where the volume is the fluid that's being infused into the patient over some period of time. Here's an example of a nasogastric tube. This is an example of a percutaneous endoscopic jejunostomy tube, or PEJ tube. As you can see in the picture, it's actually sutured to the body. This is more for long-term situations. This is a image of a feeding pump. You can see it down here at the bottom right corner. Okay, so intravenous infusions and solutions. IV, we know, I think at this point, that it means through the vein. Replacement fluids and maintenance fluids can be administered intravenously. So replacement fluids would be if the patient lost a good amount of fluids from something. Maybe they're dehydrated. It could be a number of things. Maintenance fluids would be fluids that are administered just to maintain normal levels. Infusions can be continuous or intermittent, just like we talked about before, and intermittent peripheral infusion devices maintain venous access. For intravenous solutions, saline solution is commonly used. Okay, so you're making, or you're dealing with solutions here. So remember, solutions involves the pure drug as well as some kind of solvent or diluent that the drug is dissolved in. So saline solution is commonly used. Intravenous fluids generally contain dextrose, sodium chloride, or electrolytes. So the third bullet down, we have D5W, D5/W, 5% DW. All of this is a 5% strength dextrose solution. So if you look right below it in that fraction, this indicates that there's 5 grams of dextrose for every 100 milliliters of solution. There's a typo down here on dextrose. NS indicates normal saline. We talked about that, I believe, in chapter 9. 1/2 NS is half normal saline. So if you notice the percentages over here on the right side of these last 3 bullet points, we start with 0.9%, and then half of that is 0.45, and then the last one, quarter normal saline, is 0.225% sodium chloride. All right, so infusion flow rates is going to be given, or when you calculate it, you will want drops per minute or milliliters per hour. So GTT is the drops, and MIN we know is minutes. Milliliters per hour, we're familiar with those abbreviations there for our units. So drops per minute or milliliters per hour. This relates back to when we were finding strengths of solutions. We had particular units that we were interested in. So if you recall, strengths of solutions were either grams per milliliter or milliliter per milliliter. Now when you're talking about flow rates, we want either drops per minute or milliliters per hour. Notice both of the denominators are the time. Okay, so the next handful of slides are examples of IV bags. So this is an actual IV bag, and then the next slide will just kind of have a zoomed in view of the label. Okay. So if you notice, this is a 5% dextrose, and then 1,000 milliliters is contained in the bag. So if you notice right here below 1,000 milliliters, it says each 100 milliliters contains 5 grams of dextrose, and we could figure that out also from right above. It says 5% dextrose, which we know is 5 out of 100, so 5 grams per 100 milliliters. Here's another example. This is the label for that one. So 0.9% sodium chloride, this is normal saline from what we looked at a few slides back. So each 100 milliliters contains 900 milligrams or 0.9 grams of sodium chloride in water for injection. Here's another example. This is 20 milliequivalents potassium chloride. And this one's in a combination. It says 5% dextrose and 0.45 normal sodium chloride, which is half normal saline. If you notice on this example, it actually has the similar, I'll say, values to the previous one. You see the 5% dextrose and 0.45% sodium chloride or half normal saline. But the difference was on the last slide, if you would like to go back, that one also contained potassium chloride, which is a high alert medication. So you never want to get confused when things have similar solutions, or they look similar when you're reading them. Just pay attention to all of the details. Here's another example, 5% dextrose and lactated ringers injection. And one more here, 5% dextrose and quarter normal saline. Now, the flow rate of the fluid that you're going to be administering to the patient is going to be regulated by either a gravity system or a pump system, or which is an electronic device. So electronic devices could be pumps or controllers. And then if you're not using an electronic device, you're just using the flow of gravity. An IV tubing drop delivery is not standard, so depending on the design of the tube that you're using, the drop delivery could be different from one tube to the next, so you always want to check the labels. Manufacturers specify the number of drops that equal 1 milliliter for their particular tubing, and so they'll have a drop factor listed. And you need to pay attention to this to calculate the flow of rate. So just for example, if you have one tube versus another tube, the drop factor might be 10 drops will give you a milliliter, and another tube would be 60 drops give you 1 milliliter. So this is an image for us, the primary intravenous line, and this is with gravity. So at the top here we have the IV solution in a bag, and then below that we have drip chamber. Now the drip chamber is where you would actually count the drops. So you would count the drops per minute, and then that way you can determine the flow rate. Then below that you have a roller clamp. The roller clamp allows you to either increase or decrease the flow. And then below that you have the IV tubing, which eventually leads to the patient. Now, gravity systems are actually more inclined to error because of a number of different factors. It depends on the height of the bag. If the system gets bumped, it's going to change. So there's actually more room for error using gravity. And so more so now, a lot of places are using electronic devices. So most likely you'll be working with an electronic device, a pump or a controller, and you'll have to learn to program it for whatever place that you're working at. Here's another example. You can see the drip chamber right toward the bottom of the image. Okay, here's an example of two different types of tubing. So if you notice, they do have different drop factors. On the left one at the top, it says 10 drops per 1 milliliter, and the right image has 60 drops per milliliter. Okay, so you do want to pay attention to that, like I mentioned before, the drops per milliliter for the tubing that you're using. Okay, so common drop factors are going to be 10 drops per milliliter, 15 drops per milliliter, 20, and then 60 microdrops. It's what is considered microdrops per milliliter. And that last drop factor there, 60 microdrops, that's the universal drop factor in microdrops. Here's an image of a pump. Okay, so again, you most likely would be working with an electronic device, and you would learn to program something like this. Here's another example. This is a pump that has a patient control button. So the patient, let's say the patient is getting pain medication for whatever pain they're experiencing. They could administer it to themselves depending on their level of pain, and they would just push the button and the drug would be administered. You wouldn't have to worry here that they wouldn't be able to exceed a certain amount of the medication. So there is a lockout device. So if they continue to push the button, it will not exceed a particular dose amount. All right, now time for some calculating. So the order here is 1,000 milliliters in 8 hours. So find the flow rate. Okay, so notice what we're given, 1,000 milliliters normal saline, and we want to infuse this over a period of 8 hours. Okay, so our flow rate is volume over the time. So 1,000 milliliters over 8 hours. You simplify these numbers and you have 125 milliliters per hour. Okay. Now, 1,000 milliliters of normal saline must infuse over 8 hours again. So we've already calculated this in milliliters per hour. Now we want to know the flow rate in drops per minute. Okay, so we have milliliters per hour, but we need to convert this to drops per minute. So we're going to end up multiplying by 2 unit fractions, one to change hours to minutes, and another to change milliliters to drops. Okay, so here we have it. Notice we start with our order on the left. We have our 1,000 milliliters for 8 hours. Okay, so I'll just circle it here. That was the order. And we next multiplied it by the time. So we wanted to get rid of hours and go to minutes. And then lastly, we wanted to go from milliliters to drops. So the drop factor was given. It said 20 drops per 1 milliliter. Okay, that was on the previous slide. So we multiply by the drop factor. And then we're left with the units that we want. We have minutes and drops. Okay, and then we work on simplifying our numbers. We end up with 125 over 3, which is 4.67 drops per minute. Next example. The order is 775 milliliters of 5% dextrose, twice a day, infused in 6 hours. Initially, the flow rate was set to 26 drops per minute. Okay, so this first bullet point, that's the original order. The patient needed to be infused with 775 milliliters over 6 hours, and then the flow rate was 26 drops per minute. Then, so you come in 3 hours later, and you assess the situation and you realize that the patient has received 500 milliliters and the drop factor is 10 drops per minute. Okay, so you want to now recalculate the flow so that the infusion will finish on time. Right, so notice this problem has a couple of steps to it. We first need to figure out how much of the solution is still needing to be infused, and then we have to consider how much time is left in order to infuse it, and then go from there. Okay, so we're going to take 775, that was the original amount of solution, and 500 milliliters have already been infused, so we subtract those. So what's remaining to be infused is 275 milliliters. Next, we consider the time. We had 6 hours to infuse the full amount. 3 hours have passed, so we just take away 3 from 6, and there's 3 hours left. Okay, so here's where these numbers came from. The remaining fluid is 275 milliliters, and the remaining time is 3 hours. So we want to convert this 275 milliliters over 3 hours to drops per minute. So again, we're going to do a similar thing from the previous example where we divide out the hours and get minutes, and we divide out the milliliters and get drops, and we're going to use the drop factor to calculate. All right, so we have our original remaining amount here, amount of fluid and amount of time. We multiply by the first unit fraction to get rid of the hours and go to minutes, and then we multiply by the second unit fraction, which is our drop factor, to get rid of milliliters and go to drops. Okay, and we end up with 15.27 drops per minute. And so if this is the now adjusted flow rate, then the patient will have been infused with the entire amount, 775 milliliters, once 6 hours has passed, 6 hours total. Next example. An infusion of 5% dextrose begins with 300 milliliters in the IV bag. The pump is set at 60 milliliters per hour. How many hours will it take for the infusion to complete? So notice the question. You always want to identify the question word, like who, what, when, why, where, and how, because that's going to show you what you're looking for. It says how many hours, which means we don't know the time for this example. We knew the time in the previous examples. So this time we're solving for time. We have our flow rate on the left here. So this is our equation, flow rate. So this is our flow rate, 60 milliliters per hour. And then remember, flow rate equals volume over time. So here's the volume, 300 milliliters, and then the time we don't know. So if you wanted to solve this equation for time, notice what you would do. You would multiply both sides of the equation by time. It would end up dividing out on the left here. So let me see if I can draw this for us. So if we divide out, if we multiply both sides by time, so if I multiply by time over here, sorry, this is scribbly because I'm trying to use my mouse, and I multiply this side by time as well, basically what you're left with is the equation on the bottom as soon as you divide out the flow rate. Okay, so if I divide out the flow rate, and I'll circle it again, so here we go, divide out the flow rate, you're going to be left with time, and then it's going to equal the original volume, which was 300 milliliters, times the flow rate. But notice you're going to end up flipping your flow rate over. It's going to be the reciprocal. And you'll recognize to do this because you're multiplying by the volume, which has milliliters in the numerator. And so you're going to want to flip over your flow rate anyway because you need the milliliters to divide out. So they need to go on the bottom and the hours will go on the top. All right, so we had our volume. Okay, and then we had our flow rate, and notice it got flipped over because we wanted to divide out the milliliters. We simplify our numbers. We're left with a time. Notice the unit that remains is an H for time. So when you divide out milliliters, you know you were looking for time, and you're left with a time unit, so hours. And we have that this is going to be 5 hours. All right, one more example here. If the drip rate is 30 drops per minute, how many milliliters will infuse in 6 hours? The drop factor is 10 drops per milliliter. So notice the question word here, how, and then it says how many milliliters, which means we don't know the volume. Okay, so we know the drip rate or the flow rate. We know the time, it's 6 hours, but we don't know the volume this time around. So what's going to happen is we're going to take that original equation that was flow rate equals volume over time, and we're going to solve that for volume. Okay, so you'll see it below. We have quite a few unit fractions involved in this calculation here. So we have our time. So we're solving for volume. We have our time. This is going to be times our flow rate. So this is from our equation that I just mentioned. Time times the flow rate. And then we have over here times the drop factor. And then we want to go from minutes to, or from hours to minutes, excuse me. And so we have this other unit fraction, this last one here. And then when you put this all together, notice all your units go away except for what you're looking for, a volume amount, milliliters. You work on your numbers and you end up with 1,080 milliliters. Chapter summary. Fluids can be given to a patient slowly over a period of time through the vein or through tubing, intravenous or enteral. Enteral and IV fluids can be administered continuously or intermittently. Okay, we talked about continuously, but no longer than 24 hours at a time. And then in IV solutions, letters indicate solution compounds and numbers indicate the strength. So for example, in D5W, we know that that was dextrose, and then the 5 represented 5 grams of dextrose in 100 milliliters of solution. An intravenous infusion can flow solely by the force of gravity or by an electronic infusion pump. And again, you'll most likely be using some form of a pump. Flow rates are usually given in either milliliters per hour or drops per minute. The drop factor of the IV administration set must be known in order to calculate the gravity system flow rates. So you want to know the drop factor based on like the tubing or however you're administering this medication. Microdrops per minute are equivalent to milliliters per hour.